All right, so far we've talked about either an atom absorbing energy as a photon or releasing energy as a photon. Now we're going to talk about electrons. So electrons can interact with the atom as well. They can strike the ground state and give the atom some energy. So in this case here, we had mentioned before that the photon energy must be exactly the same. In this case of 12.8 electron volts, it has to have more than enough energy to make it jump. Any excess energy will just be passed as a passing electron. So let's take a look at this. So it says 12.8 electron volts arrived from the outside atom. It strikes the electron at ground state. We're using that same diagram again for this question. So if you look at the ground state, it says we're starting off with, going back up, 13.6 electron volts. All right, so if I kind of quickly draw this out as a quick reminder, we're going to have ground state, and that energy at this one was negative 13.6 electron volts. All right, so an electron comes in, and it has 12.80 electron volts coming in. It's going to give all of it as it possibly can to the atom until it can't reach the next step. So if you think about what's happening here, we have all these different energy levels that we saw before. We're going to see how much energy is this thing going to have. If it reaches somewhere between those two transitions, so not quite to the next step, what's going to happen is it's going to fall down and only use whatever energy is actually needed. So think of it as almost like a step scenario. So the way I like to think of this is the energy levels are like steps. If I give something energy and it has enough, it will reach to that step. If I have just a little bit more, oops. Let's erase that previous line too. Oops, undo. I'll redraw it. Steps. So if it has enough, it'll make it. If it has a little bit more, it doesn't have enough to reach that next step, it will still continue to fall down. It will never reach that next step until it gets higher than that step. So it basically has to have more than enough energy to reach this n equal value. So we're going to see where it's going to end up. So if it uses the maximum amount of energy, 12.8, let's see where it would reach. So let's say that our change of energy is 12.8. And my initial value is negative 13.6. So let's see where that final value would be. So once again, the change of energy is equal to EF, final, minus initial. In other words, EF is then going to be the change of energy plus the initial energy. So 12.8 plus negative 13.6. We end up getting negative 0.8. So I'm going to go back up to the other diagram. And I'm just going to erase some of this stuff here. So 0.8 is where it ends up. So that means 0.8 is somewhere between 0.54 and 0.85. So it's going to end up somewhere between these two. Okay, it doesn't have 0.54. If it did, it would reach n equals 5. But because it's going to be somewhere between, it actually falls back down and only goes to n equals 4. Okay, so let's see if I can recreate that on this question here. So here's my ground state. N equals 1. Here's n equals 2. I'm going to make them a little bit further apart so you can see n equals 3. N equals 4, n equals 5. So this electron is going to jump all the way somewhere between these two and fall back down onto this one because the energy level of this one was our negative 0.85. And it doesn't gain that much. It only gains between those two values. So it doesn't quite make it to the next energy level. which we said was 0.5, sorry about this, 5.4. So it doesn't make it to 5.4. It only goes between those two values. So in other words, where does it go? Well, it actually only goes to n equals 4. So it says, what is the speed of the electron after this interaction? Well, because it should go to 0.80, but it only goes to 0.85, there's a difference of energy there. The electron will leave with the excess energy. So it's going to leave with the difference between. Okay, so it's going to, the energy of the electron is equal to, well, the energy it said it had minus what it actually took. So in other words, here we are dealing with 0.05 electron volts of energy. Well, what speed is that? Well, that speed, if we're talking about kinetic energy, we can then make it equal to 1/2 mv squared and then solve for that velocity. The only issue is this needs to be in joules. So assuming the maximum energy, what is the speed of the electron after the interaction? Well, in this case here, we're going to go 2 times the energy divided by mass, square root, or 2 times 0.05 electron volts multiplied by 1.6 times 10 to the negative 19 joules per electron volt, divided by the mass of an electron, 9.11 times 10 to the negative 31 kilograms, and then we're going to square root that. And I get a speed 1.33 times 10 to the 1.33 times 10 to the 1, 2, 3, 4, 5 meters per second. Okay, so a quick summary of our concepts here. So it says success to the Bohr's model improves upon Rutherford, making it by describing the lowest energy of the atom, making that the atom stable. The Bohr model successfully describes the line spectrums of a hydrogen atom. The Bohr gave us a basic understanding of why emission and absorptions are produced. Failure, it wasn't actually able to predict anything other than hydrogen, only one electron atoms. So in other words, basically hydrogen. The model also does not explain why some lines are brighter than other lines. But otherwise, Bohr's model is a great adaptation from Rutherford's model, once again, fixing those problems that we saw in the past. All right, so try the questions that you see below. Once again, you can skip over the ones that talk about the 2 pi r type of questions, focusing on the ones with emission and absorptions.